Good afternoon, everyone, and thanks for joining us for this CSCAN InfoCAN webinar with our newest corporate member, Oracle Labs. I'm going to let you know that we're recording this session and it'll be up on our website, on the CSCAN website in a few days. And what I'll do is I'll introduce our speakers and then I'll hand it over to them. And Liza and Yasha will take care of questions and answers as well. I also want you to know that CSCAN InfoCAN is putting together a database for people to submit, for students to submit their resumes so that we can pass them along to our corporate members. And there'll be more information about that on the website later this week, but I'll make that announcement again at the end of the session. So for now, I want to thank Liza Barnett, who's the team lead for university recruiting at Oracle Labs, and Yasha Pushak, who's a senior member of technical staff in the AutoMLx team at Oracle Labs. Yasha is a graduate of UBC. He did his PhD there. He also was a member of the CSCAN InfoCAN board as the first representative for students on the board, and he finished his term last year, I believe, right? So I'm going to take myself off camera and hand it over to Liza and Yasha.
Hi, good morning and good afternoon to everyone. Like Adele mentioned, my name is Liza Barnett. I'm one of the recruiting team leads for university recruiting efforts here in Canada. Really excited to be with you today and have Yasha share his experience and a little bit more about the exciting technologies we are working on. One of the things that we do want to make sure is that we're staying connected and introducing our opportunities for both internships and full-time in Canada to you all. So I put a link to register in the chat. That is the first way for us to, like I said, stay connected, be able to reach out to you about our opportunities, and also we'll send you directly to where to apply to those roles. So please register through the chat and I will hand it over to Yasha. Thank you.
Okay. Thanks, Liza. All right. So as everybody knows, these days, companies tend to have a lot of data. And many of those companies may even have a business problem that they'd like to solve with that data. The trouble is, most of them don't actually know how to go about doing that. So traditionally, this is where machine learning comes in, or the data scientist pipeline, as you might call it. Right? So you've got this data set, and you got to hire this data scientist who's now going to do a bunch of stuff with your data to produce this machine learning model. But of course, this takes time, and there's a lot of different questions that they have to answer. For example, which model should you use? Are the features in your data set good, or at least good enough? And which hyperparameter configuration should you use for this model? And answering all of these questions, even for seasoned data scientists, can be both expensive and time-consuming. And it's also quite tedious. Oftentimes, the answers are different, but not that different. Of course, once you have this model, then you need to figure out whether or not you can actually use it, right? And so this is where it comes back to the business use case. Can you actually trust your model to do a good job for what you care about, right? Or is the model actually fair, with some meaning behind that word fair there? And in some cases, especially in the business world, it matters whether or not your model actually meets regulatory requirements, right? In some cases, users actually have a right to explanations for what decisions were made using their data. So this is where the AutoMLx pipeline at Oracle comes in. So in this case, we take in this data set. We automatically deal with all of those questions for you. Which model should you use? Which features should you use? Which hyperparameter configuration? And we output an optimized machine learning model. And then from there, we help you answer all of your questions about using your model using explainability. So automated machine learning is by no means a new topic. In fact, the first work on this was coined as combined algorithm selection and hyperparameter configuration. This was done by some people at UBC back in 2013, and they released a tool called AutoMLx, which basically seeked to do the first half of what I just described on the previous slide. Since then, there have been a number of different packages and methods and various approaches that have been proposed: AutoSKLearn, AutoKeras, H2O, etc. The vast majority of these are all based on Bayesian optimization. Essentially, this tries to exploit trading off between exploiting configurations and regions of the model's that are known to do well versus exploring new things that haven't been tried before. Another common approach, a little bit less common, but still frequently used, is genetic optimization, another black box optimization solver. You can improve the running time of these methods with various tricks, essentially trying to weed out and eliminate poorly performing models and configurations quickly. These come in the form of things like successive halving or hyperband, which are both very well known and popular. And of course, they can be combined with these search procedures as well. Oracle's approach is a bit different. In particular, we have what we call an iteration-free pipeline. So the dataset comes in, we do some pre-processing, we select an algorithm or a model, we sample the dataset, we identify the good features, and then we pick a good hyperparameter configuration for that model. And importantly, we never go backwards, right? The step never happens. So we don't deal with this combined problem, this big combinatorial optimization problem. Instead, we employ a whole bunch of heuristics, which allow us to quickly search this space and speed up the process. So the first stage in our pipeline is pre-processing. It's pretty standard. We just look whether or not there are lots of missing values in the dataset. If there are, we either drop or impute them, depending on what's more appropriate in this case. Then, if there's a high cardinality categorical variable, we'll use label encoding so that we can convert it into an integer value. Or if it's low cardinality, we'll use one-hot encoding instead. We can also automatically extract meaningful features from date-time features so that we go from this date time into a column with year, month, day, etc. And then finally, we use a standard scaling on the numerical preprocessors. None of this is particularly custom. It's all fairly standard. And of course, in some cases, you can get better results, but you usually need domain knowledge to do a better job in this case. So advanced users can always bring their own preprocessor if they'd like to. The next stage in our pipeline is algorithm selection. So this is about trying to identify which model works best. So if you're familiar with it, we essentially are facing the no free lunch theorem here, right? No single model works best in all applications. And so in this case, what you can see is we've identified across a bunch of different data sets that different models perform best in each case. And so this really motivates why we need to actually select for a certain data set which model we should use. And we do this in a fairly novel way. So essentially, first of all, what we've done is we've learned what we call these proxy model configurations. And this is an offline stage that we did before we actually look at any new user's data set. So in this case, we have a whole bunch of existing data sets that we've already collected. We train a bunch of different random configurations for each of our different models. And then we've evaluated which of these different hyperparameter configurations works best for each of these different model families. We took the best one and we say we're going to use, for each model, we took the best one. And then we say we're going to use this particular hyperparameter configuration as a representative for how good this model family performs. And these are what we're calling the proxy models, because we're using them as a proxy to understand the strengths and weaknesses of each different model family. Then when a user brings their new data set to us, we then train each of these proxy models, which of course can be done in parallel on their data set. And we can very quickly get an estimate of how good each model family is for solving this particular data set problem that we have. Using that, we can then select the top machine learning model algorithm. From there, we move on to our adaptive sampling stage. So in this case, really what we're trying to do is reduce the size of the data set so that we can speed up the subsequent stages of the AutoML pipeline. So in comparison to things like hyperband or successive halving, where they start off with usually small problems like small data sets, and then they progressively increase to larger ones, what we've observed is that realistically, at some point, you actually just have enough data. And there's no need to keep moving to larger and larger data set sizes to make sure that you're getting the right answer. You can just stop. So what do? Essentially, we start off with aggressively subsampling our data set down to a very small size. We run the selected proxy model, get an estimate of how good it is, and then we just keep increasing the size of the data set. Once we've observed that the scores are plateauing and not improving, we stop. And we pick that data set size and we say, all right, this is enough data. The model doesn't really need much more information than this to do a reasonably good job. Now, this is important because in our next stages, we can speed things up. So for example, in our featured selection stage, we have somewhat similar motivation, except in this case, instead of trying to reduce the number of rows in our data set, we're trying to reduce the number of our columns. So in this case, we'll use the output from the previous stage, again, using this subsample data set and the proxy model. And we'll start evaluating which features work well for this particular problem. The goal, again, being to reduce the number of features so that we can speed up the performance of the or speed up the training time of the algorithm without reducing the performance. So our method starts off by ranking the different features. And we have a number of different ways that we do this, 5 in total. So this looks at, for example, the correlation between each particular feature in the data set and the target, and then ranks the features using this or various other methods. Once we have these different rankings, we then evaluate the different, or we then come up with a bunch of different feature subset sizes, and we increase these exponentially. Now, again, you could view this as a large, hard combinatorial problem, right? Because you could try to sample any possible combination of feature subsets. But instead, we just take our feature ranking orders, and then we start peeling off the most or the features that we believe are the most useful one at a time, using these increasing sizes of feature subsets. We then evaluate each of these feature subsets by training our proxy models on them in parallel, which gives us an estimate for how good each feature subset is. And then finally, we can just review all of the scores, pick the best one, and identify our final reduced data set. So we now have something that can use to train our models very quickly. All right, so this brings us then to the model tuning, or the hyperparameter configuration stage in our pipeline. And this is usually the most expensive part of our pipeline, because we have to actually evaluate a whole bunch of different hyperparameter configurations, which is why it was important in our previous 2 stages that we reduce the size of our data set so that we can speed this up. Again, as I mentioned, by far the most popular methods for this are based on Bayesian optimization and genetic optimization. Now, both of these are black box optimization techniques, and the choice of these methods essentially implies that this is assumed to be a challenging optimization problem, quite likely with a whole bunch of suboptimal local minima that the optimizer can get stuck in. But in fact, we were wondering whether or not this actually makes sense, right? What if the responses to these parameters of these algorithms are actually just quite simple, maybe even unimodal? So as a motivating example, suppose that you want to bake a cake, right? And you have this temperature parameter, which you can control to either increase or decrease. Now, intuitively, you can expect that probably you're just trading off between too little or too much, right? I mean, if you know that your cake is burning at 700 degrees, you probably don't want to try 1,000 because that's also going to burn, right? So there's no need to explore that part of the search space. So the work that I'm describing here is actually work that I did as my PhD, which was independent and in parallel to the work that I'm about to talk about on the next slide, which is done at Oracle Labs. But you'll see the connection in a moment. So what we did is we studied a very closely related problem, algorithm configuration landscapes. In particular, we looked at 193 of these individual algorithm parameters, and we found that 99.5% of them were statistically indistinguishable from being unimodal. And that's really cool, because that means we should be able to exploit that. We also have another paper, which is currently under review, on AutoML loss landscapes, right? So this is the exact same problem that we're currently discussing here. And in this case, we looked at the full landscapes, right? These are the combinatorial landscapes between 8 different machine learning models. And what we found is that 75% of them, all but 2, were, again, statistically indistinguishable from being unimodal. Now, for those remaining 2 cases, the deviations from unimodality were very small, less than 0.03%. And so what I mean by that is that there's a small number of hyperparameter configurations that if you were to change how good they actually performed, you could make the landscapes appear to be unimodal, or at least to become indistinguishable from being unimodal from a statistical perspective. So here's an example of one of the landscapes that we observed for a single parameter for XGBoost, the subsample parameter. So what you can see is that the response to changing this parameter, right, how good it is actually incredibly simple and incredibly smooth with respect to the parameter, right? On the one hand, it's very low, and on the other side, your performance is at first very quickly and then very slowly getting better. Very simple to optimize. Now, of course, not everything is quite as simple. Here's an example where we saw something a little bit more funny. I like this one. It kind of reminds me of like a children's slide, how you can see it at first speeds up and then goes down and then speeds up again. But in any case, still relatively simple to optimize, still unimodal. And while we did observe, again, a few other small exceptions to this, they were not common behavior. All right, so why am I talking about my PhD work instead of what I did at Oracle, or what's been done at Oracle? The reason is because at the same time, independently in parallel, Oracle was working on a novel hyperparameter tuning strategy. the right-hand side here. So those two orange lines are the estimates of the directions of descent on this function. And they're doing this just by evaluating two different configurations that are near to each other and then seeing the slope. They then find the intersection of two of these gradients that point towards each other, and they heuristically jump all the way down towards that intersection. And they repeat the process in this much smaller region around this place where they believe that the configurations are going to be better. And that's essentially how it works. They repeat. At the same time, all of these other hyperparameters are being searched in parallel, and they're updating the values of all the other hyperparameters whenever new values that are better come in. And this turns out to be both very fast and very efficient. So this work that I've described so far was published a couple of years ago at VLDB. So the main results here is that they did this analysis comparing this AutoML solution to two state-of-the-art competitors, H2O and AutoSKlearn, both very widely used, very widely cited, and quite competitive out there. What they found was that actually our solution is performing better on average. So in the top plot there, what you're looking at is the average ranking across these 30 or 50 or so data sets. And you can see that overall, we're usually the best, have the best answer, regardless of the time budget, right? So these are going all the way down to 10 minutes. We're able to find better solutions than anyone else. On the bottom plot there, this is just an example of the actual scores for the final 60-minute time budget. And you can see that, again, we're getting quite a bit better solutions compared to the competitors. But importantly, we're doing this in quite a bit less time. All right, so we now have this magic learning box where we just feed in some data and out comes a trained machine learning model. But now we need to use it in the wild. And of course, all kinds of questions come up. Can you trust the model? Did it learn something reasonable? Is it fair? Or does it meet my requirements? So of course, you can rely on inherently interpretable models. So these are linear models, for example. In these cases, these models are very simple and very easy to understand, right? If you know that the coefficient is -2 for one of the features, then an increase to that feature will change the prediction by exactly twice in the opposite direction, that value. Super simple, super easy to interpret. And you can extract the notion of feature importance, if you'd like, by looking at the magnitude of each of these coefficients. Another model that you could look at are decision trees, right? These are so simple that you can actually draw them on a piece of paper like this and perfectly understand what they do. Again, very easy to understand, very easy to explain, and you can again get a notion of feature importance if you're interested. But what about non-interpretable models, right? So these could be more complex models where you can't just immediately extract some information from them like this, or they could even be proprietary models where you're not allowed to open them up and look inside and see what they've learned. So this is where the MLX part of what we do comes in. So in this case, we take in a machine learning algorithm, we take in some data sets, and we analyze them. We modify the data, see what the model predictions look like and how they change, and then we output some explanations. So I'm going to talk about two of those different kinds today that we have, which is a subset of what we have. And these are feature importance and feature dependence. So let's first talk about a global or model level feature importance. So in this case, you're going to start off by perturbing one or more features in your data set. Right? So if this is our data set here, these features, if they're good features at least, they're all going to be somehow linked to the target that you're trying to predict. But we're going to change that. We're going to shuffle all of the different values for this particular column, thereby unlinking that feature from the target. Now, if this feature was actually useful to the model, then we should be able to see that its predictions get worse. So what we do is we perform inference, right? We obtain new predictions, which should no longer be as good as the original ones. And then we analyze this and see how much worse does the accuracy of the model get after we've changed the data set. And we repeat and average this for the different columns. So what I've just described so far is known as permutation feature importance. And in fact, this method was first proposed in the paper for random forests at the end there. But we can also apply this for individual predictions, right? We don't just have to do this for the full data sets. So in this case, we're doing it on a row-based level, where we're actually measuring the change in the prediction instead of the change for the entire data set or the accuracy. And these gives us local or prediction level feature importance explanations. So let's take a look at what these actually look like. So in this case, we've got a global or model level feature importance. So this is for the Titanic data set. So we're trying to predict whether or not a passenger on the tenant died or survived based on their features. So in this case, you can see that the single most important feature was the sex of the passenger. And so you can see the average feature importance as the bar, and then as well, we can also show some 95% confidence intervals as those whiskers. The local feature importance predictions are actually a little bit more nuanced. So in this case, we see both positive and negative feature importance. So what does this mean? In this case, what we're actually seeing is that the most important features are still the ones with the largest bars. But in this case, because it's a negative, this means that knowing that the passenger was third class meant that the model decreased their survival probability by approximately 30%. In this case, you can see that knowing that the passenger was female increased their survival probability by about 23%. So you can see you can get very detailed and nuanced information from these explanations now. But the question remains, how do you actually perturb these features, right? How do you change them? So the most common method, and some people recommend, is to sample from the feature's marginal distribution. This has the advantage that it's very fast, and that features that are ignored by the model are not important. I'll come back to that on the next slide if you're not sure what I mean. But it does mean that we're evaluating the model on data points that are actually out of the training distribution, which can be sometimes problematic. And the reason for this is because we're not only unlinking that feature from the target, but we're also unlinking it from other features, which it may be correlated with. An alternative approach to this is to sample from the feature's conditional distribution. So in this case, we're essentially trying to preserve the relationship between the features while still as much as possible unlinking that feature from the target. This is slower because it takes more work to actually link the other features. And some people argue that it should never be used because the duplicate features that are actually used by the model are considered unimportant in this case. And again, I'll come back to that on the next slide. However, it does evaluate the model in the data distribution. All right, so let's talk about the interpretation of these. Essentially, if you're using marginal sampling, the interpretation is knowing how much the feature impacts this particular model's predictions if it doesn't get to know the value of the feature. With conditional sampling, it's more like asking how much does this particular feature contribute towards this model or a retrained model's ability to predict the target. So let's use a motivating example to dig into why. So in this case, we have a very simple data set, right? Each column is perfectly linearly correlated with the target. So either of them are perfect predictors of the target. But our model has learned it's only going to look at a single feature because it prefers solutions that are sparse. So in this case, according to the model, the only feature that it needs is x0, not x1. So if you use marginal sampling, what you learn is that but with conditional sampling, what you actually see is that neither of these features are important. Why? Because when you modify feature x0, you don't actually modify it, because if you do, you break the relationship between x0 and x1. So you keep it the same. And the same goes for x1 when you try to modify it, which means that neither of these features are important. And in some sense, this is true, right? If you have the other feature, it doesn't matter, because a retrained model could have learned to use the other feature because they contain duplicate information. So how do you actually perform conditional sampling then? Essentially, you use k-nearest neighbors. So in this case, if we're going to replace the age feature in the data set, we would condition on the weight feature in this data set to find similar values for the age. So we're going to sample a new value for age for that red point there from these blue values. And you can obtain these values using k-nearest neighbors. The problem is that k-nearest neighbors is actually exponential in the value of k for large high-dimensional data sets, which means that this conditioning step is very slow. But then on the other hand, at the end, we just replace it from using a single random neighbor. So our observation was we could actually swap these two steps, perform the samplings first and then the conditioning second, which allows it to be substantially faster. But of course, it does also decrease the stability of the method. So we've added a novel stratification strategy that allows us to reduce some of this variance. So how does this work? Essentially, first of all, we start off by building a KD tree to group similar data points by leaf. So if you're familiar with stratified sampling based on the target, this is essentially the same thing, except instead of ensuring that we have equal representation from the target values, we ensure that we have equal representation from groups of similar data, right? So each leaf in this KD tree is going to be similar. We then do our projection. We randomly sample down to one case of our data set, stratified by leaf. And then we only have to find the single nearest neighbor in this case, which is much, much faster, right? Building this KD tree has a very small overhead. It's roughly n log n, where n is the size of the data set. And of course, it's amortized over iterations if you do this multiple times. And then this final step is, again, much faster, because now we have one kth of the data to perform, which speeds up k and n in terms of preprocessing. And then finally, we're reducing our exponential complexity from 2 to the k minus 1 down to 2, so constant. Again, when we usually use k equals 20, this is a substantial running time speedup. All right, so that's great. Now we can explain both what features are important to the model, what features are important for the data set on a whole or could have been used by the model, and we can do this on both a global and local level. But on the other hand, you might still be wondering, what does the model actually learn, right? What is it really doing? Feature importance may not be enough. So in the context of this linear model, we could actually immediately say that if you changed the features for a particular prediction, you would understand exactly how the model would respond. So what if we want to have some kind of feature dependence explanation for these general machine learning models as well? We can provide that as well. So in this case, what we do is we start off with our data set. We take one of the columns and we fix every row in that column to be a constant value. So we're again modifying our data set. And then we perform inference. So we now see, what do the model predictions look like when we've modified this particular this. In this case, for a continuous feature, you can see the age feature there is on the x-axis and the probability of surviving the Titanic is on the y-axis. So you can see that the model has learned something quite reasonable. Children were more likely to survive and the elderly less so. On the top, we've also added in the marginal distribution of the age feature, because sometimes you will notice in these pictures that the model is doing something really weird over on the edges. And that can be because there wasn't enough data for the model to have learned the real relationship that actually happens there. We can do the same thing for categorical features. In this case, we represent it as a bar plot, or as a bar chart, sorry. So you can see the females were more likely to survive than males. Now you can also do this for 2 or more features, right? So in 2 dimensions, the original proposal for partial dependence plots was to show it as a heat map like this. Now this is useful, but it can be a little bit hard to understand, right? So the probability now is encoded using this color channel, but it's a little bit difficult because it's hard to see whether or not young males are actually more or less likely to survive than middle-aged females. So in this case, you might be able to make it out. Middle-aged females are more likely to survive the Titanic, according to the model. But there's another way that we could represent this that allows us to much more easily see this information. And that's actually just by swapping the color channel and the y-axis in this case. So now we've once again put the probability of survival on the y-axis, and we put the much lower cardinality female feature on the color channel. In this case, you can very easily see that young males are just slightly less likely to survive than middle-aged females. This also allows us to actually plot the confidence intervals on these bars, which gives extra information that simply isn't available in the heat maps. And the advantage of this is that you can now see, for example, that if the model looks at a particular person who is both male and old, the confidence interval is very small. And that means that the model doesn't need to know anything else about this person to be quite confident in its prediction that they're going to not survive the Titanic. On the other hand, if you're an older female, the model has a larger confidence interval, which means that it's still paying more attention to the other features about that person to make up its decision about whether or not they died or survived. And up at the top, we can also show both the joint and marginal distributions for the data set, which is something that's not as easy to visualize for the heat maps as well. Now in higher dimensions, traditionally, there wasn't really a solution to this. You could, of course, look at multiple lower dimensional heat maps, or you could just look at a table, but neither of those are really great visual representations for higher dimensional partial dependence plots. But we've come up with a solution to this that extends our previous ideas. And so this uses column faceting in this case. So in this case, what you see is that we have two different plots, essentially two subplots, one for females and one for males. So in this case, you can also notice that we've actually swapped the color channel and the column facet. Again, the reason for this is that the column faceting channel is much less expressive than the color channel. So we've put the lowest cardinality feature on the column faceting channel. We've also changed the colors that we're using. So we've gone from this blue-orange category encoding to an orange to pink category, which represents the fact that this new feature, SIBSEP, which is the number of siblings or children that the person has on board, is actually integer valued instead of categorical. And this allows us to see some very nuanced information. For example, for this pink line that you see down the bottom here, there's this unexpected trend reversal, right? So what this means is that the model says is that if a woman has a large number of siblings or spouses on board, then they're actually more likely to survive if they're old than if they're young. And that doesn't really make a lot of sense. There's no good reason why we would expect that to be the case. And in fact, quite likely, oops, wrong way, it's because there was no similar training data, right? So you can see up in this distribution here that there are no pink values for older women, which means that there weren't any older women with lots of siblings or spouses on board. And so the model's just doing something weird. All right, so that concludes the portion of the talk on both automated machine learning and how we can explain the models that we're producing with it. If you have any questions, I can pause here. Otherwise, I've also promised to give a quick comparison from my perspective of academia and industry.
I just have one question, Yasha, right now, but please feel free to again put those in the Q&A or chat so we can get them answered. And don't forget to register so we can stay in contact. If you like what you heard, we have many more opportunities to do things just like Yasha is doing for an intern or full-time. So the first question that I have is, are there any empirical validation of feature importance performance, example, top N of Oracle AutoML output SOTA approaches like SHAP and LIME?
Right, so one of the tricky things with actually comparing explanations is that there isn't really usually a ground truth answer that's correct. And in fact, the correct answer really depends on what you're trying to do, right? So in the case where I was talking about marginal versus conditional sampling, the right answer really depends on whether or not you want to learn about exactly what the model is using or exactly what the model could have learned, right? The real world, what relationships are out there. And so in the absence of real ground truths like that, it's very hard to say SHAP or LIME or permutation importance is the best answer, right? And in fact, our approach isn't to say any one of these methods is the best. It really comes down to your particular application and what you want to be able to learn. So rather than comparing them to each other, we have opted to try to support as many different diverse algorithms as possible. So I focused in this presentation on permutation feature importance, both local and global, because they're very popular and easy to understand, but we do support the other methods as well. So if our users have need for them, they're certainly able to do so.
Perfect, two more. KD trees can be very expensive if you have a large number of features like in text. Can you comment on it?
Yeah, they're not too expensive for large numbers of features, as I understand. So the basic algorithm for the KD tree is that it's basically like a binary tree. So except instead of always working on the single feature in a binary tree, you just pick a random one each time. So at each step, you pick a random feature, and then you partition the data that you have in two groups. And then next you move on to one of those groups and you recurse. You pick a new random feature, you partition it according to that feature into two groups, and you just keep going until you're done. So in fact, the number of features doesn't actually impact the time complexity of building a KD tree at all. It's completely independent. All that matters is the number of rows that you have.
Perfect. And then this question, I might need a little bit of clarification, but Jennifer asked, this talk is called I Have Data and the Business Problem, Now What? Can you talk about that? It wasn't really touched on.
Sure. So lots of users come with data, right? Or business users, they come with data. But the problem is that they don't know what they actually want, or they don't know how to make use of that data to solve their business problems. And so that's where the methods that I've been talking about come into play, right? So if you don't have the machine learning expertise on your team and you're not able to hire someone to do so because, quite frankly, that expertise is in very high demand, that's where these solutions come in, because now you can use automated machine learning to automatically build a model that can solve your problem. And then you can use the explainability methods that we've described to actually understand whether or not that model has learned something reasonable for your particular application and to meet your regulatory requirements in terms of being able to explain what the model has learned.
Perfect. I don't see any additional questions, but again, feel free to add those to the Q&A if you have any. And then, Yasha, if you want to go over the academia corporate piece, and then we can always circle back if I see any more.
Sure. Yeah, feel free to ask more questions at the end. So first of all, I want to start off with a big asterisk here. These are my personal observations about the differences between academia and the industry, and they may not represent your own. As well, this comes from my lens as having been a PhD student, so grad school versus industry, and in particular here, I don't mean any industry job, I actually mean doing research and development, and in particular, my experience again comes from Oracle Labs. So some companies may be different. Nevertheless, one of the first differences that I think is easy to identify is the working pace of the environment. So especially in grad school, you usually have very few deadlines and they're quite spaced out. And so one of my lab mates joked to me a few years ago, well, I submitted my paper, so I'll see you next month. And we both laughed, but at the same time, he also said, I wish that wasn't as true as it is, because really he was going to take some time off just because his paper was done and he'd worked a lot on it. On the other hand, in the industry settings, you have a lot of deadlines, right? These are very frequent, they're very short, and in fact, they often change a lot too. And so sometimes one week you'll be working on something and it'll be the most important thing, and then the next week your supervisor comes to you and says, drop that, this is the new most important thing, work on this instead. And then you try to get back to the old thing if you have time when you can. Another big difference is about collaborations. So this can vary, but at least for me and for many of the grad students that I know, you don't usually work with a lot of other people, other than, of course, your supervisor or supervisors. And one of the main reasons for this, especially as a PhD student, is that you need to prove that you can be an independent researcher. And so if you're working with all these other people, then it becomes hard, especially at your defense, to be able to say, this is exactly what I did. These are my contributions and not theirs. On the other hand, in a team setting, like an industry research environment, at this point, you have a team of people. And if you're successful, that means your whole team is successful, and vice versa. So in cases where you're not able to get something done in time, it's perfectly reasonable for you to ask for help from your supervisor or those around you for important tasks so that you can all meet that deadline and share in your team successes. And at the same time, these two items actually can interplay between each other. And so one of the first things that I observed when I was an intern, as I just speculated at one of my meetings with my supervisor, I said, you know, I've identified this interesting behavior in our data set, but I wonder what it would look like if somebody was trying to attack the system in this, way. And a week later, he thought that was a good idea. So a week later, he had new data for me where he had asked one of my teammates to actually simulate attacking the system in that precise way. And now I had the data to look at, which is a completely different experience than in academia, where if you wonder open-ended questions like that, you're kind of out of luck unless you can find the data online. Another difference between the two is customers or users. In grad school, these are usually limited if you even have any at all. In an industry setting, you do have them, which of course has two sides to it. On the one side, you need to do work to make them happy. On the other side, when you do work that you're proud of and you share it with them, you can also get to see that they get excited about it because they see all the ways that they can use that. And that can be really cool because you see people being happy about the stuff you've done. Whereas in grad school, if people are using the work that you've produced, maybe you've released some open source code, you're usually removed from them. So you never get that feedback and you don't see that result. Another one of the differences is on the primary output of what you're trying to produce. So in academia, this is papers, right? If you don't publish, I mean, this old saying, publish or perish, right? And to some extent, That's true. In an industry setting, it's a little bit different. At least for us, our primary output is actually code that implements our research. And when we do have new ideas, the primary focus is set up on patenting. But at the same time, papers are still encouraged. And this is something that I'm quite happy about. In fact, I was talking about this with my supervisor the other day, and he said, well, he was talking about some of the stuff that I was considering publishing with his supervisor. And the answer was, yes, definitely do it. If you've got good results, let's publish. We should be doing it. So that makes me quite happy to have found a situation where I can still publish and do research, even though I'm in an industry setting. Another difference is on running time. So in academia, theoretical complexity, I mean, it's, there are empirical works as well, but theoretical complexity is often important. And so in particular, I'm thinking of one paper that I looked at as a PhD student, where in the title they said fast and efficient, because they had a theoretically fast way of solving this problem. But at the same time, they still said for n greater than or equal to 3, it becomes prohibitively expensive to run, so we just don't bother. And that was kind of funny to me, because I looked at their implementation and I realized that it was all using basic Python data types and for loops. And that meant that it was unnecessarily slow. So I re-implemented it using NumPy, and I don't even know how big of it a speed up, because I was now able to run it in a few minutes for n equals 13. And this was an exponential thing. So way faster, right? and that was pretty cool. And this kind of thing, even though that was purely a software engineering trick, is really important in industry setting. Because if you can make the code run 100 or 1,000 times faster, then that means that you are literally saving your customers 100 or 1,000 times the cost that it takes to run this code. And that's important. Reproducibility is another big one. So in academia, it's really important that your results from your scientific studies are qualitatively similar, right? Good science is repeatable, something that we've all heard before. In academia, in the industry, this is one step farther, right? So it's not just about repeating similar output, but in many cases, there's actually a requirement that you can reproduce exactly to the number the results that you've got. So you now need full quantitative reproducibility of all of your results, which can be achieved in many cases by carefully fixing and controlling the random seeds that you're using. Another one of the differences is on computing resources and your access to them. Now, this can vary by lab and supervisor in an academic setting. If you're lucky, you may have a dedicated cluster for your lab. Or if not, perhaps you can get access to Compute Canada or some other resources like that that are shared in your department. But it depends on who you are and what you have access to. Not everybody has access. In an industry setting, at least in a job that's similar to mine, you can pretty much expect that you're going to have access to a dedicated cluster. And of course, if you're at a cloud company like Oracle and you need more cloud resources, you can, assuming you can justify it, you can get them because, it's available. Datasets and applications is another very big difference. So in academia, you can use pretty much anything that's open source. But sometimes that's limiting because you don't have access to large real-world data sets, which means that you can try to rely on artificial things. This has, trade-offs and limitations. In the industry settings, you have this advantage now that you can work with larger data sets that you just may not even have access to, and you can only do certain things with these large data sets that you couldn't do in the academic settings. And at the same time, you also get to have a real-world impact with the work that you're doing. But there is a flip side to this. So that is the licenses. In academia, you can use anything that is open source. In industry settings, this is not the case, right? You must get approval for every single data set that you want to use. And some data sets you won't get approval to use. And this goes for both code and data, which is actually really important. Because in some cases, some data sets have very restrictive licenses, which mean that if you actually so much as run your code on them, you now are legally obligated to open source your code. And of course, if that code is proprietary software that your company is very invested in, that can cause all sorts of problems. So it's very important to pay attention to these things in industry settings. I think one of the big ones that most people wonder about is research freedom. But I want to actually argue that this is not so different from academia, right? In academia, at least as a grad student, you can work on anything that you can convince your supervisor is exciting and interesting to work on. And the same is actually true, at least in industry settings like in Oracle Labs. And the reason for that is that Oracle Labs will be happy to work on any research problem that could conceivably make the company money within the next few years, right? So I assume if you're working at a small startup, this is probably not the case because they have very limited scope. But for large companies like this one, the labs department or the research department that you're working in, the whole purpose is to invest money in research to try to keep the company competitive, which means that if you can make a compelling case for why your research might help with that, then you should be able to get approval to work on it. Finally, the big one that I want to talk about is failure. So this is a big difference, right? In grad school, it can be very just keep getting rejected, or maybe you don't even bother submitting papers because you just know that your results look bad and everything you try just isn't working out. That can be extremely discouraging. And I've been there. The first 2 years of my PhD did not go so well. I ended up abandoning my first research project and moving on to something completely different. Well, okay, not completely, but quite different. Still, not a fun experience. In an industry setting, it's actually very different. And in fact, I've heard from quite high level management that failing is good. And in fact, it's encouraged, because in a research industry setting, if you're not failing, if none of your teams are failing with anything, then that means that they're not taking on enough risk and they're not trying things that are going to make the company money and be useful for the company. And so failing is a measure of success, right? The key thing is, of course, try not to sink all of your time into things that fail. You don't want to keep failing for years and years and years. Just fail fast and then move on to the next thing so you have a higher chance of success. And I think this is a really big one because from a psychological perspective, it makes a really big difference on how you view your work and how you view yourself when things aren't working well. All right, so finally, if you're interested in learning more about what it's like to work at Oracle Labs or anywhere at Oracle, in fact, we are a very global company. So here on this map, I'm showing all of the stars where our labs offices are based. So you can see that I am based in Canada, over in Vancouver there, that red star. But we have quite a few different teams. So I am on the first team on this list, the Automated Machine Learning and Explainability team, but we have many others. So if you're interested in learning more about them, please visit the link on the top of the page where we have a description for each of these teams, or just send an email to us and we can get an application process started for you for Oracle Labs. And now I'll pause again in case you have any questions.
So a few questions came through. I'm going to go to, can you view the peer reviewers of your papers as your customers in academia?
Sorry, can you repeat the question?
Can you view the peer reviewers of your papers as your customers in academia?
Oh, okay.
And here's the second part. Hold on, here's the second part. Let me give you this. In academia, if you build systems for users in your research, they could also be considered users in industry sense.
Yes, that's true. So there are definitely cases where academics get feedback from real users, right? There are projects that you can work on in academia where you're actually working with people. But I think that's relatively uncommon, right? It certainly depends on what kind of research you're doing. But for all of computer science, I think the normal situation is that you don't have that direct feedback. And you can view, I suppose, reviewers as being users in this sense that are giving you this feedback. But I wouldn't say that that's a great experience, right? I mean, reviewers, you talk to them for your one review process. Maybe you iterate a little bit if there's a rebuttal phase, but they're not actually going to use what you're doing. They're just trying to judge whether or not it's technically sound and worthy of being published. And sometimes you upset them because they have a related paper and you didn't even cite it. And how could you dare not cite their very important and cherished paper? And from there, you're on the wrong foot already, right? Because they don't have a vested interest in your success. Because if you're successful, that means even that they're not successful. Whereas with real users, if you're successful, then that means you've solved their problems. So it's not exactly the same experience. I think they're pretty different.
Perfect. And the last question that I got was, what if I use AutoML with 10-fold cross-validation? The model found different families of classifiers on different folds. How does one standardize the final pipeline to be used in such a case?
Okay, so in fact, our default setup, and this is configurable by the user, does use cross-validation. But instead of running a separate AutoML pipeline on each fold, we actually use those folds internally to the pipeline. So when we're evaluating each of our candidate models or hyperparameter configurations, we internally use, say, 5-fold cross-validation to get 5 different estimates for how good that model is. And then we take the average and we choose the one that gets the best average performance across those 5 folds. Rather than treating the AutoML procedure itself as if it's a single model. Although, of course, you could try that. I've never thought about that before. From a computational point of view, like, it's going to be a lot more expensive, which probably means that it's not going to be worthwhile. Although you could, if you really wanted to do it, then consider ensembling the output or something like that to produce an ensemble. One of the reasons why our AutoML solution does not rely on ensembles, though, compared to other competitors like AutoSKLearn, which do use these ensembles and they actually combine all of the best models at the end, is because it's just more computationally expensive, right? Then you have to train all of these different models, and the advantage that you get from it is usually very marginal compared to the running time speedups that you get from just sticking with a single model in the first place.
Wonderful. Well, thank you so much for sharing your knowledge and wisdom on all topics today. We really appreciate it, Yasha. Again, excuse me, if you have heard anything that you were interested in, please use the link in the chat to apply to our jobs. We will collect all of your information and be in touch with you to make sure that our recruiter is talking to you about next steps in the process and any interest that you have. And then we will, of course, circle back with Adele to also get your CVs and stay in touch that way. So thank you so much to Adele, and thank you all for listening. We really appreciate it.
And thanks very much, Yasha and Liza, for today's webinar. We will be uploading the recording to the CSCAN InfoCan website and send an email to all CSCAN InfoCan members to let you know when it's there with the link to it. And I want to thank Oracle Labs for taking the time to make you two available for our membership today. So thanks, and thanks to everyone for attending. Take care.